And then we can, yeah, okay, let's just make it set up. Yeah, that should be right. So let's just consider what happened last night. Presumably that this flying object is moving across our top of us. So basically, we have what happened last night is that so we saw the flying object. We saw the flying object, which is travels at a certain velocity, and presumably it's very fast, very fast. This is velocity. And I say with velocity is vector, but in this way we only consider the simple case, which is a straight line motion. So basically, the orbit is a straight line, so we don't bother to denote the direction, knowing that it's moving to one direction. So that's the issue. So basically, so if we just consider, okay, this is our x-axis, this is the position, okay. This is origin. This is origin to make sense simpler. And on the other hand, you can imagine that we can introduce we can use the coordinate system, which is moving together with the object.
Yeah.
This international, how to say, international space station? What to call it?
Space station, yeah. International Space Station. Yeah.
Station, yeah,
Or
international.
the ISS, I think that's a bit snappier.
Okay. ISS, SS, okay.
Yeah.
Okay, that's fine. It's fine. Yeah, we're doing the same thing, okay. Now, just make things simpler. Can we just consider that the speed is fast, which is so fast, actually, and could be faster than it really is. So this is a condition given. So this is given condition. So velocity is, relatively speaking, it can reach, let's say, 0.6 speed of light. So c is the speed of light. Speed of you know the speed of light of how the number?
No, I don't.
That speed of light.
Okay.
So
very fast.
After, yeah, very fast. Well, of course, we just make things more apparent because we want to see something. Now, question is, and if I use my watch here to say this is 9 p.m. or is 9 p.m., can we just reset that? We just make things simple. Okay, we just say this time says t equal to 1 local time. Okay, it's second. And the question is, we're wondering that we're wondering because at this particular moment, this coordinate, this x coordinate, I just put a prime there because the flying is a flying. So we just make things simpler. That at this particular moment, these guys they just crossing. So this prime to xy is overlap with 0. In other words, you can imagine that flying object is just at this particular case, they are just the same position in terms of their position, no matter which coordinate you use. Of course, next moment, the flying object will be somewhere else. Okay.
Yep.
So next moment, they will change. So I just wondering. So given that, and given this velocity, and also the time, according to my watch or a digital clock, that whatever, it is 1 second. Okay, and time is 1 second. Yep. The question is, what will be the time? The actual time. So the time, what would be the time? That's something is very is in relativity. The local time, I should say, the local time. The local time. Can we go to t prime? That time is read by the astronauts that they actually use their watch. Okay. Yep. So they are also counting the time all the time. Okay. The only difference is that their clock is moving. Their clock is moving, and our clock is not moving. It's fixed. It's fixed on the ground. Okay. Okay. That is scenario. So that is a question. That is condition. So let's just introduce Einstein's formula. Okay, that's a very famous transformation. So because basically Einstein argues that this is T in general, according to Einstein. So relativity, special relativity. Are you reading? Did you say you are reading special relativity?
Oh no. I recently I watched a film in which one of the major sort of plot elements is the dilation of time. That's what I was referring to.
Well, that matters.
Was the slowing of time.
That's reading. So basically, says the Einstein says that the time he predicted that the time would be different. It's other way around. It's the logical consequences of their. How about my voice? So I recently found the microphone voice volume getting down. Is that compared with last week? It's okay.
It sounds good. Yeah.
Oh, his volume is good. Oh, that's good. Okay, that's probably just back to normal. Okay.
Okay.
So how do we? So that is a consequence. That is logical prediction that the two time will be read differently. But how can we do that? So to do that, you have to really put the space time together. So that's another concept is called space time. Space time is that to treat the space and time as equivalent. So the space time can be described, the position in this vector, the position vector can be written as this is like ct, and that is x. And again, c is speed of light. Okay. So basically, what it says that this time, the time between the local time and this is in the frame, so on the ground. So this is a space time on the ground. On the ground.
Yep.
And this is space time. This one, can we just put a prime here, x prime here? That is a space time on the station, so on the International Space Station. Okay.
I can feel the matrix coming on.
So that is matrix come on. Yes. So how to so the question is how to convert relate these two space time. Space time is just a single word, it's new words. Okay, they just say, well, you cannot talk about the time and space separately. Okay, we agree. So the importance is how do we connect these two? How do we connect this the space time in the ISS with our space time? Okay, can you guess what we can do?
According to our knowledge, apply a matrix transformation.
Yes, apply the matrices. That's right. So you need to put 2 by 2, right? It's 2 by 2.
Yep.
So coming to the A, B, C, D. Yes, that's it. That's called the transformation. So that's a big deal. So these matrices, these matrices called Lorentzian transformation. Lorentz transformation. Just called Lorentz transformation. Lorentz transformation. Okay, it's a particular transformation which just governs the reading of your space, your space time relative to another flying object, a flying frame. So this can be considered flying frames or flying object or flying frame. So it's change. Now, what is ABCD? So Lorentz transformation in this case. So what is ABCD? So Lorentzian transformation. Can we just put a name here? This Lorentzian transformation. That can be written as simply written as gamma. Just rewrite that. It's gamma. It's 1 and 1. It's simple. And negative beta and negative beta. I double check that. Yes, that's right. Is that simple?
Yeah.
So that's Lorentz transformation. But the question is, what is gamma? What is beta? So basically, that is by definition. So I write down here. So beta is defined as the ratio of velocity over the speed of light. Can you see that?
Yep.
So in our case, if substitute our velocity, the 0.6 c divided by c, what do we get? It's just a number.
Yeah, 0.6.
Yeah, 0.6. Got it?
Yep.
How about the gamma? Oh, that's a big deal. The gamma is called the Lorentz factor because that was attribute. It was introduced by Lorentz, so they call it Lorentz factor. It's called Lorentzian. Yes, belong to Lorentzian factor. Yeah, factor. I hope after this introduction, you can watch some short videos on the YouTube, okay, to see what is it.
Definitely, definitely.
So this gamma by definition is simple. It's just 0 equal to 1 over square root 1 minus beta square. Do you have calculated? Let me just work out this gamma factor. I have
yes.
yeah. Okay, you want to
So
try?
one over, sure, 1/1 take
So yeah,
0.6.
yeah, beta square. You can beta square is 6.
Oh,
Yeah.
so the square root of 0.4. Actually, sorry, my calculator is so bad it can't even do a square root.
Okay, I can
I
do
might
that.
have to
I
turn
can
it
do
over
that.
to you.
0.6 square. I can do that. Equal to okay, 0.96 take away. What's difference anyway? That is 0.64. So we have to find the square root. Okay, I have square root 0.64. Oh, lucky is 8. Is 8. So it's 8. So it's 1/8. Okay. It's
Okay.
1/0.8. Sorry, 1/0.8. Can we convert that into integers? That is 1 divided by 0.8. Oh, not too bad. Not too bad. The 1.25. Not too complicated. Okay. Now, could you construct the famous Lorentz transformation by using this information?
I think so. Okay,
Yeah.
let's give it a go. 10, yes. So that would equal our Lorentzian factor is 1.25, and our new matrix is 1, negative 0.6, negative 0.6,
Yes.
and 1,
Yeah.
which would equal.
Yeah. No, we can stop here. We can
Okay.
stop here. We
All
can
right.
stop here. We can stop here. You can distribute that. You can distribute 0.5.
Mhm.
Yeah, we can distribute that. Yeah. But I prefer this form because it's simpler,
Okay.
right? It's simpler.
Okay.
Doesn't matter. So after all, you have to always multiply the Lorentzian factors. Now it's time to answer our question. So our local time is 1 second. Okay. 1
Yes.
second past particular times. 1 second past 9 p.m. Whatever. It's just the local time. So we are interested to know what would be the time, the t prime actually happen. This time interval for 1 second. What would be the case for the internet at international spaceship? So therefore, this x prime. Now we have a very reason to argue that at this moment, these two frame overlap. So therefore, we can see that x. So in this condition, so at this particular point, x equal to x prime. Okay, 0. Just equal to 0. Makes things simpler. So what we're looking for is called Lorentzian transformation multiplies 1c, okay, because c is just 1c over 0, okay. Now, can you spend some time to I can simplify this better. Can we just make this x equal to 0? Oh,
Yes.
there's hang on, let me see. There's no guarantee you can point because that's a very big issue. You cannot, make the judgment, pretending you know both sides. Okay, so perhaps I put a question mark here. Perhaps this is not very strict. Okay, because we're only interested in the time. Okay, what is time taken? So perhaps we just keep this there as it is. Okay, we don't have to assume this more. Yeah, perhaps it's more in-depth consideration. You will consider whether there's two coordinates equal to 0 simultaneously. We don't. That is more complicated. Today, just demonstration. Can we just keep the x prime here because we are only interested in the t prime? Okay.
Yep.
So can we just finish? Can you work out this one analytical formula for this the vector on the other side?
Sure. So that's a case of just matrix vector product of the Lorentzian and the original vector.
So eventually we're going to have the single column. We're going to have a single column matrix.
Okay. Right. And does that mean that the Lorentzian factor you can do that last and ignore it in the beginning? Can you multiply everything at the end?
Yeah, multiply this at the last. Yeah, that's why you don't.
Okay.
That can make it simpler. Yeah.
Yes. So that's going to be okay. That's going to be 1 times c.
Yeah. 0 and then
yep. Oh, yep. See, plus 0. Oh, yeah, plus 0.
yeah.
And
Can we
then
simplify? Can we save some space without writing 0?
okay. Okay, let's just call that C then.
Yeah.
And then the next one's going to be negative 0.6 times C,
Yeah.
plus 1 times 0. So it's going to
Yeah.
be C negative 0.6 C.
Yeah. Okay. Okay.
Yep.
And then you multiply Lorentz factor at this point.
Yes, which is going to equal 1.25 C, and then 0.6 times 1.25 is 6 times.
You are Einstein now.
You're
doing Einstein work.
It's negative. It's going to be negative 1.6 times 1.25.
Yes, I
What's
think.
a quarter of
Yeah.
6?
Yes, it's right. We should keep the x prime undefined. That's the transformation too. You see, any judgment, any debate, or how to say it's called a paradox, arising from the conflict conclusion made by observer on different frame. Okay, so that's why I made the same mistake today. I just subjectively assume that these two coordinate overlap. I can't because I am on the ground. Okay, I can't make this decision. We have to rely totally on the Lorentz transformation. So which we can see. That's become apparent. Okay, what would be the t prime? Finally, what would be t prime?
1.25 multiplied by negative 0.6 C.
No,
right.
You just compare the constant. You just cancel the C. Can you see? Because they are the same. Okay. So what I can write down here, perhaps you didn't see that exciting moment. See this? What you have to see? We have by doing so we have obtained this very simple result. So this vector you can consider is space-time is vector. Can you see? Space-time is vector. Space-time is vector, or to code it. By our definition, this vector that has been solved by after Lorentz transformation. This is 1.25 C, okay? And that is negative 1. Can you see?
I see.
So if you compare, so what does that mean? That C t prime will equal to 1.0 equal to C multiply 1.25. Can you see that result? So if you cancel the t on both sides, you regard the clock reading from the
and it's just 1.25.
Is that straight?
Yeah.
So that clock, their clock t prime is longer, 1.25 second. Can you see the difference? Can you see that?
Yes.
This guy or me, I mean, last night my clock that just naps about exact 1 second. However, for the guy over there, the clock is long time is longer. It's 1.25 second.
I see.
So that is a special relativity. Time dilation.
Excellent.
Yes, time dilation. Yeah, I can write down here. So this phenomenon is called time dilation. The big deal. Time dilation. Okay, I think that is a good example to utilize the
very good example. Yeah.
To use the transformation concept to solve it.
Excellent. For sure.
Okay. Let me just. Of course, you can see. Without a subjective judgment, we realize that the position cannot be 0. It must be negative 1. You see, so we must completely follow that Lorentz transformation. So once you accept Lorentz transformation is a transformation, to get the reading, the time and the position, then you have to accept that. You have to follow that. Okay.
Yep.
Okay, another issue is that perhaps this is time for us to go back to what we call the simultaneous linear equation. Simultaneous.
Yeah, I've never quite understood
Yes.
systems of linear systems of equations.
Yes. Yeah.
I mean, I kind of understood them, but it's apart from calculating how many apples and bananas one needs to buy.
Yes, that's right. Yes, you have bit functions. If you have the shop, if you factories, you will count that outcome based on the cost of product. Okay, it is economy,
Yes.
right? You if you want to you say synthesize some some particular drink, right? You buy water, you buy the juice, you buy any other chemicals, and you make the metrics to predict the final product. Okay, the cost of matter. That's the metric. This is something we can use. But as one of classical starting point to introduce metrics and eventually the building the linear algebra is come from solving a simultaneous equation, right?
Okay.
So what is linear equation? So basically, can you write any question? What is a linear equation? What is a linear?
Yes.
So that is SLE.
Yeah.
So what is LE? So what is LE? Can you just write an equation which is a linear equation?
Yeah, sure.
Yeah, that is a perfect in linear equation.
Yeah.
But yeah, that's right. We just reform that. We write that basically what we write is put fx here, okay, and minus y, and equal to b. Can you see this transformation? This just is algebra. Can you see? That is how we do it. That is so in general. So this is a linear equation. So basically, if you just use a slightly different notation, we can say can we so this is can we say we'll talk about coefficient afterwards. Okay, but this equation only involved two unknown. Can you see? You got two unknown. Can we solve this question? Do you think we can solve this? Can we find x to y from this single equation?
No.
No, impossible. So according to algebra, the independent equation, the number of unknown must be the equation independent equations must be required. N independent equation must be required to solve n unknowns. So that's why in this case we only have one. So we have trouble. So what we can do that normally that is this question is it can be solved according to the principle we described. So you can solve the two equation. You see, can we solve another equation? So another equation. Can we use m prime x plus y equal to b prime? Can you see? So in this way, we obtained a simultaneous equation. So that is question one. So that is question two. So in principle, we should be able to solve this question.
Yep.
I'll give example. So this is we'll go back to the notation. We can improve this notation afterward. But before we go, can we just use the example we used last time? We just go to the example we used last time. For example, if you have a negative x and 4y plus 4y equal to we don't know the e over there. Do we know the vectors? No. Hang on, I have to find an example for you, which will give you a nice. Okay, let's go to this example, which will give you a proper integer. It's the same because I don't want to. I try to avoid using the decimal and the fraction. So that is 3x minus 2y equal to 1. Another is negative x plus 4y equal to 3. So these are example of simultaneous equation, okay, with two unknown. Do you know how to solve that without use metric? Do you know how to solve that?
Actually, the only way I've recently looked at this is to make a what's it called? To put it all in a matrix and then do elimination.
Okay, now this time, can we just use the, because we're going to gain, today we're going to gain some insight from the algebra manipulation,
Sure.
algebraic manipulation of simultaneous equation. So can we just do that? Can we just copy that here? Can we call the equation 1, equation 2? So to solve that, I just demonstrate. So 1 is called to, the method is used called eliminate, okay? So basically we can from 1, so step 1 from equation 2, we can solve the x, can you see? So x can be solved. So x will equal to 4y minus 3. Can you follow me? We just rearrange the equation 2.
Yep.
We call this equation
Put it all
3.
on one side.
Yeah, we put x because we just want to eliminate. So this is a 3. So what I will do next is we substituting equation 3 back into another equation, into equation 1. So in this way, we can eliminate to what in order. So what is the purpose? To eliminate. So that is the purpose. I wrote down here. Substituting this one to eliminate. X. Okay, that is agenda. That's our agenda. Yes, indeed. If you substitute that one, we got 4y minus 3. Can you see? Minus 2y equal to 1. Right? Can you see? So x disappears. X disappears. So that's 1. Now the question, can we solve this y in the y equation now? Can we call it equation 4?
Yes.
Yes. Can we do some housework?
Yes.
So that is
yes.
That's 7. Can you see? You can help me. Can you just
okay. So
can we solve this y?
So we've got,
because it's algebra.
12.
Okay.
12. What's that? 12y take minus 9.
Yeah.
Minus 2y equals 1. So wait up. I'll put it in. 12y minus 9 minus 2y equals 1, which is equivalent to 10y take 9 equals 1.
Oh, that's beautiful solution.
Equals 10.
I can see the solution now. Y is the unit. That's great.
Yes.
That's why I accumulated some problems so that
yes, nice integers.
So you can enjoy use integers, without touching the. Oh, it's great tradition in mathematics, that pure mathematics, and they only deal with integers. Okay, they hate decimal, they hate fraction, but reluctantly accept the fraction. They call the rational number. Okay. But they never allowed the irrational number into their the realm. Okay.
Yes.
So anyone talking about square root 2 or pi will be punished. Actually, one of the saga says one of the students of Pythagoras was drowned because he claimed that he found the square root 2. So people around, yes, he put in the water.
Very unhappy.
Very unhappy. Oh, this happened to me again. They just give me the warning.
That's okay. All good.
Yeah, okay. Or 10 minutes, we'll do it again. Doesn't matter. Okay.
No worries.
So we'll save that in case. Okay. All right. Lucky, we got y here. Can we just do? Can we, in order to find the x, what can we do? We do substitution.
Substitute y.
Yeah. Yep. We substitute 4 into what? We have formula for x already. We just double check. We have formula for x. Which one?
That would be. Let me just have a look. Oh no, do we have a formula for x? Yes, we do. X, 4. Yeah, 4 times 1 take 3. Okay, so it's formula. 1.
So that's why we substitute into 3. Okay.
Yep.
Okay, what is x?
X is also 1.
Oh. That's great.
Yeah.
That's good. That's good. Oh, yes, x is 1. Can I write down here? So x equals to 1. That's a good news. And life is simple sometimes.
Yes, occasionally.
Occasionally, yes.
Yep.
So
x equals 1.
Yeah. Oh, great. So solve the problem.
Sorry. Yep.
Now let's do some exercise. Can we just transform that into matrix?
Mm-hmm.
Can we transform this equation into matrix as we did before?
Yes.
That is how matrix actually that's how matrix was originally introduced. Okay. There are
Mm-hmm.
some mathematicians that just figure out, well, this limitation method perhaps too difficult for layman, you see. But in the
Yes.
meantime, I wish more people can use our mathematics to solve their real problem. Okay, what can we do?
Yep. Yep.
Develop the algorithm. Okay,
Uh-huh.
these
I
keywords
see.
in computer programming. Algorithm is nothing. It's just
Yes.
it's just a very practical method to work out the result
Mm-hmm.
without knowing it's simpler, much simpler. Okay, can we do that? Can we do
Yep.
that? Can we just transform these two simultaneous question into this is two simultaneous linear equation into a matrix
Yes.
form?
Yes.
Okay.
Yep. So that's going to be 3, 3, -2.
Yes, that's coefficient. That's called a coefficient matrix.
-1.
In this case, you don't use that what we call it. We put this name last time. It's called what we put them three together. What is that form? What for the name?
Yeah, I forget.
Yeah.
Okay, so well, that's
we
going
don't. We don't at the moment. We just put the coefficient here.
to. Okay.
Yeah.
Yep. And then that's going to be.
That form we used last week will be used to actually solve this problem without actually calculate the inverse. Okay, because inverse for some people are too difficult. So that's why next week we're going to talk about a very important manipulation method called Gaussian elimination or Gaussian Jordan elimination. Have you heard of that?
I have, yes.
Oh, good. So, yeah,
yes.
good. Gauss.
I've only heard of it. I haven't done it.
Gaussian Jordan. I probably primarily could go to Gaussian. Jordan was Jordan, Jordan, right? Elimination method. Elimination. Yeah, we'll talk about that one. But today we're trying to find the similarity. Now, if we just read this form, can we give me the hand? So that is x, y. And how about other side? How about the left hand side? On the left hand side,
just one. This is 1, 3.
Yep, that's right.
Yep.
So without using matrix, we have found x and y. See, we have found x and y. Do you want to double check that? Do you want to check? So basically, to check. Oops, not to check. Oh, to check. So what can we do? So left hand side, we're equal to. Can you do some exercise? 3, 1, -2, 4, multiply 1, 1. This is our solution, okay? We just double check if this algebraic method is correct.
Sure. So that's going to be 3 plus 3 plus -2.
Yep.
1 plus 4 equals 5. Oh, that's
different.
No, that's not right.
That's right.
Yeah.
What's wrong here?
What have I done here?
Yeah, we double check that. How about the y? Y is 1. Okay, we solve the y. Y is 1. What's going on here? So 3, 1. Negative. Hang on. I just found the negative sign is wrong. I just check. Can you see? This must be negative.
Yes, -1. Right.
So can we do it again? So this is -1. What would happen?
Yep.
It's -1 here.
-1. Okay, so that's going to be -1 plus 4 is still -3.
-2.
Sorry. Yep.
-1 4 times. We have trouble, right? We have 3 multiply 1 and -2. That's 1. X is 1. And why is that? Why is not? Why is -1 multiply 1 plus 4? That is 3, right?
Yeah.
It's 3.
Yeah, it should be. That should be 3.
Yes.
Yeah.
Well, let's just do some checkup. So we double check that. So basically, what we from the equation 2, we have x equal to 4y minus 3. Okay. We substitute that, we could equal to 3y, 4y multiply minus 3. And we expand that is 12. This would be 9. That is 2y. 2y take away 10. 10y, yeah, y is 1. It's right. It's correct. What's going on here? So basically, we have x and y is 1 1. What's going on here? So 6 3 times. So that's interesting. See, there's some error here. Yeah, we just check again.
A bit strange.
It's a bit strange there. So 3 -2 -1 4. Yes. Oh yes, yeah, we are right. What are you looking for? We are looking for this guy. We got it. We're looking for this guy. We're looking for this guy. Can you see? We found it.
Yes.
Yeah,
Yes.
it's correct.
Okay,
Absolutely.
good.
Nothing wrong.
Yes.
It's perfect. Okay. So you can see.
Excellent.
So this is a good example that you don't have to use metrics. Okay, you don't have integer matrix. So the operation you introduced here, I just write down here. I just copy this formula. This is very good example. I just copy that as 3x minus 2y equal to 1, and that is -x plus 4y equal to 3. Okay. So what you have done here? So basically, we don't have to see. We don't have to introduce that matrix method. Okay, because we have proven that we have proved that it is equivalent. But my point is that still I would like to do some comparison. So this is a algebraic form. This algebraic form. Algebraic form. This matrix form. We just see what kind of the operation we can introduce to manipulate matrix from the knowledge in our algebraical form or algebraical row or axioms matrix.
Yep.
So that is a matrix form, -1, -2, 4, yes. That is x, y, and that is 1, 3, okay? And so what we do is say, so basically in these two equations, we can do no number of things. One thing is that we can actually, for example, we can multiply the two. You see, if we multiply 2, so equation 1, we can multiply any number. Can we multiply the 2 here? So that will give us 6x minus 4y equal to 2. Can you see? This second one is not changed. Second unchanged. So this is